I'm Mikko Heikkilä. This is a short introduction to our paper, Differential Private Markov in Monte Carlo, and this joint work with Jonas, Onur and Antti. Now the main question in the paper is how to run Mcmc with privacy. And in this presentation, I'll skip most of the details, so you should check the actual paper as well. So let's start with Mcmc. So a common problem in Bayesian inference is that the posterior distributions tend not to be available in closed form. And one general solution for this is to use Mcmc to generate samples from these distributions. And here's a very simple Mcmc algorithm. So we are sitting at some point in space. We have a proposal distribution that we use to propose the next value for the chain. And then we have an acceptance test we use to decide whether we should move to the proposed value or stay put. And with some assumptions, we then have guarantees that asymptotically we'll end up with the samples from the correct distribution. The second component is differential privacy, which is this nice mathematical definition of privacy. Looking at the definition, we have some random algorithm M, depending on input data D, giving some output S. And what the definition says is that if instead of data D, we had used a bit different data D prime, then the probability of seeing the same output is almost the same. And in our case, what this roughly says is that if we see an output from a DP algorithm, let's say from a DP acceptance test, then from the output, it's hard to tell whether any given individual was present in the training data or not. So it basically guarantees some level of deniability for individuals. And what we are really using is something called Renyi differential privacy, but the basic idea is the same. So here's the main thing. We want to sample from the posterior while guaranteeing some privacy. Since we already know that Mcmc can have this built-in randomness in the acceptance test, let's try to use that for privacy. So on the next slides, I'll first derive a DP acceptance test using full data on each iteration, and then another test using data subsampling. So starting with the full data version, what we need from data on each iteration is this. So it's just log likelihood ratio plus log prior ratio times the proposal ratio. And I'll write these without thetas from now on. What we use in the paper is something called Barker acceptance test, which boils down to this formula here. So we calculate the delta from data, add some standard logistic noise, that's the vlog, and see if the result is positive. If yes, then we move to the proposed value, otherwise we stay put. And this satisfies detailed balance, so you'll end up with the correct distribution asymptotically. Now this logistic noise is a bit problematic for privacy, so what we really want is actually some Gaussian noise instead. So let's do this. Take some normal noise and add some correction variable, such that the sum is close to the standard logistic. And assuming this can be done, then we can approximate the Barker test like this. And the point is that this Gaussian noise now guarantees some privacy. And as for the corrections, in the paper we propose to generate these using a Gaussian mixture model trained for this task. So this is the DP acceptance test using full data. Now with DP, data subsampling can be used to improve privacy. And this because subsampling introduces more randomness to the algorithm. So let's try to add subsampling to the private acceptance test as well. Now the quantity we'll need from data looks like this. So B is here the mini batch, N full data size, so it's just an unbiased mini batch estimate of the previous delta. And we want to approximate the same Barker test as before on the right hand side here, so full data delta plus standard logistic noise. And we would like to do an approximation that works as before, so starting from the left, adding some Gaussian noise for privacy and possibly some corrections as well. Let's write it again in steps. So we want to find the missing steps here. We can first use our previous trick to decompose the logistic noise to get this far. And I've still left the variances in some doubt, but let's fix those later. And now to continue, let's assume the central limit theorem holds. So we can argue that delta star as an unbiased estimate of delta is actually equal to delta plus some approximately normal noise. And that gives us something like this, which still looks messy, but actually the only thing missing now are the variances. So let's fix those as well. And matching the variances, we finally end up with these two approximations, the first based on the central limit theorem, and the second on this logistic noise decomposition. And with that, we're actually done. So what we do in the paper is formulate these two DP acceptance tests, one using full data and one using mini batches. And there are also important assumptions I haven't mentioned, but you have to read those from the actual paper. And here's the link to the paper. And with that, thanks for watching and go check the paper as well.